And be sure to tell me if I gave you too many points. If you want more points taken off, tell me. I'll take them off. All right.
So close.
So close.
To what?
Harrison had an issue with a really complex math problem called 5 minus 1.
Okay, well, I literally had to write on the back of that page because I did it wrong, and then I looked at it and I went, what am I doing? So I restarted the whole problem, and then I got like really tired of doing it, so I just kind of went fast.
So 5 minus 1 became something other than 4.
It was 3, I'm pretty sure.
Okay, so let's go ahead and get started on sequences and series. So the first section in this chapter is kind of a little bit of an overview of each of them. So we'll talk a little bit about sequences, a little bit about series, and then we're going to get into more detail in the subsequent sections. So this first section is just an overview. Now, of all chapters in calculus, sequences and series, for most people, they feel like this is the hardest topic in all of calculus. It's a topic that no individual idea is difficult, but it's because there's so many ideas that go on that make it challenging. Like it'll feel like I get it, and all of a sudden you don't get it. Like it's kind of like juggling. Juggling 3 balls, no problem. You throw in a 4th, oh, I got it. Then you throw in the 5th, and everything falls to the ground. So it's one of those subjects that you really need to stay up on it. If you don't stay up on it, it's very easy to completely sink. So of all chapters, don't get behind in this chapter. So start your 10-1 homework tonight, 10-2 homework tonight. And the ideas behind series are, they will come back again. This is not a subject that is just a one and done. When you get to differential equations, you will see that there are infinite series involved in differential equations. If you go on, and it depends on what kind of curriculum you end up doing, but if you do partial differential equations, there will be series behind that. If you do complex analysis, whatever you do in the future, if there's advanced math, there's going to be sequences and series embedded in there somewhere. A lot of upper level physics too will have series involved. Okay, so starting out simple, we're going to talk about a sequence. A sequence, when we say sequence in this class, we mean infinite sequence. If it's a finite sequence, we'll make extra note of it. It's a finite sequence. Okay, so when you hear the word sequence, you want to think of something that has an infinite collection of terms. It's kind of like the word log. When we hear the word log, 99% of the time we mean natural log. And if we want to talk about a log other than a natural log, we really make it explicit. Log base 3, log base 5. But if someone just says log form, usually they mean put it using natural logs. So it's that same kind of idea. When we say sequence, you should be thinking of an infinite list of numbers. Most of the time, these indices here are going to be natural numbers. So positive integers from 1 on up. Most of the time. You can change your indices to be slightly different if you want. I'll see you later.
You'll see me later for whatever it is.
Yeah, 4:05 or 4:10 or something.
It's on my calendar.
Yeah, perfect. Hello. So a sequence again is just a list of numbers, and that list of numbers usually is going to start with an index value of 1, almost always. We'll see a couple examples where it's a little different, but almost always we start at 1. So notationally, we will write our sequences either as an explicit formula or with some sort of recurrence relation. That's how we're going to generate the terms in the sequence. This one is more important for us. That's primarily what we do in calculus classes. Recurrence relations happen sometimes, and we'll look at some of those, but usually we are not going to look at them so much in calculus. There's a really famous sequence that is defined with a recurrence relation that all of you have heard of. Anyone remember? What sequence do you know that you've heard of over the years?
Fibonacci?
Fibonacci sequence. So that one is defined as a recursive sequence because you take two terms and you add them together to get to the next term. Right? So that's what it means to define a recurrence relation. You get to the subsequent term by doing something on the prior term. Whereas when we look at the more common way to generate the terms of the sequence, we are going to define them with a function. So in other words, you take the index and you are going to build some mathematical expressions based on the index. So that's going to be called a function. Yeah.
So all the sequence is doing is just you're predicting a certain point at this time at a random time in the future based on a function.
Yeah, it's not even, I wouldn't even say prediction, it's just a list of numbers, and we're creating a formula that creates that list of numbers.
So it can help you predict.
It's going to tell you what any term is that you want.
Okay.
Yeah.
So you could, like, this is useful for like data gathering stuff. If you gather enough data, then you can make a
You can make a function that
formula to
tells
predict
you.
it in the future.
Yes, that is very true. That is very true. Now, typically with sequences, we don't think of it from that prediction point of view. We're just thinking of a way to sort of classify how to build each term in the sequence. So, well, we'll look at an example in 1 second. So, recurrence relation, subsequent term is based on the prior term. Okay? Explicit formula, term is based on the index value. So those are the two differences. This is the general notation that we use for sequences. 99% of the time, we just say that. It's understood that n goes to infinity. If we had a finite sequence, we would somehow make that really clear. Okay, when we're dealing with this explicit formula, it's obvious that we're dealing with functions because the index value is some mathematical expression that's based on the index value. It's a function of the indice. Okay, so it could be n squared. You would take the index value, if it was 5, you would square it and get 25. That's going to be the term value. So you take whatever the index value is and you do whatever the mathematical formula is. But it's a function. The one thing that's different is that most of the functions you all dealt with are continuous. Right? There's no gaps. When you think about this function, the domain is discrete. 1, 2, 3, 4. The domain is discrete, which means that the function is not continuous because you don't have a function value at 1/2 or at pi or at any other number other than these natural numbers, positive integers. Okay, so it's discrete. So when you look at the graph of a sequence, it's just a bunch of dots. For example, the harmonic sequence, most important sequence probably that crops up in this chapter. The harmonic sequence, this is the notation for it. If we just write that, it means, n starts at 1 and goes towards infinity. You don't have to write that. We're going to understand that that's true. And you can see that a graph of the sequence, it's just a bunch of dots. Right? So it's discrete, it's not continuous, it's a bunch of dots. Many times your sequence function can be a subset of a continuous function. So 1 over x is a continuous function, right? Smooth function, no gaps, 1 over x, no gaps on its domain. Sequence 1 over n, lots of gaps. But this sequence is a subset of this continuous function. And we're going to see that that can lead to some theorems shortly. So, for example, taking the limit of a sequence. So we all know kind of the general idea of a limit. So if you have a sequence and it's getting closer and closer, we usually use the expression arbitrarily close, meaning infinitesimally close, meaning as close as you can possibly imagine. If it gets arbitrarily close to some number as you go further and further out in the sequence, you're going further and further out in the sequence, if it gets arbitrarily close to L, then we say the limit of the sequence is L. All right, everyone have that basic limit idea? So as you go further out in the sequence, the terms are getting closer and closer and closer and closer to L. And so when we look at this sequence, the limit of this sequence is 0, because the y value that these are approaching is 0, and it's getting arbitrarily close to 0. This sequence never becomes 0, but it's getting as close as you can imagine. You know, and as you go further and further out in the sequence, you can kind of think of it as becoming indistinguishable from 0. When you're out at 1 divided by 500 million, it's pretty close to 0. So the same idea of a limit that you used in Calc 1. The big difference is that in Calc 1, you had some techniques to evaluate limits that involve derivatives. And you all know that you can't take the derivative of a function unless it's at the very minimum continuous. You can't take the derivative of a discrete function, right? A function has to be smooth, has to have a tangent line in order to take the derivative. So there are some techniques for evaluating limits of sequences that we will go back to continuous function land where we can take derivatives. So if we can show that our sequence is a subset of a continuous function, that continuous function is differentiable, maybe we take a derivative. L'Hopital's rule. Has anyone in here not heard of L'Hopital's rule? So L'Hopital's rule is usually a very easy technique if you have an indeterminate form of 0 over 0 or infinity over infinity. We'll get to it for sure. You should have seen it in Calc 1. And so this harmonic sequence, 1 over n, the limit is 0, because those fraction values are getting closer and closer and closer and closer to 0 as n gets larger and larger. And that, again, is the harmonic sequence. We can also generate another type of sequence that's very similar to the harmonic, called the alternating harmonic. And a lot of these, I'll put the Desmos commands over here in case you want to play. Desmos is really good for looking at sequences and series. So I'll put the stuff over there just so you know how to do it if you want to do it on your own. So the alternating harmonic, 1, negative 1/2, positive 1/3. So it's the harmonic, but every other term is negative. We call that sign changer part of our explicit formula. We usually refer to it as the switch. So it's just switching signs from positive to negative, back and forth, all the way through. So when we say alternating, we literally mean alternating. It can't be plus, plus, minus, minus, plus, minus, plus, 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 minus, minus, right? Alternating means plus, minus, plus, minus, plus, minus. Right, so that is what we mean. You can have sequences that have weird distributions of pluses and minuses, but they're not called alternating. Alternating literally means every other term is negative. Here's a picture of the alternating harmonic, and its limit is also 0. Right? The terms are getting closer and closer to 0. So even though there is oscillation, the magnitude of each term is getting closer and closer to 0. So the limit of the alternating harmonic is also 0. And in general, when we're finding limits, if the denominator is increasing and the numerator is constant or maybe just toggling around between a couple of values, the limit is 0. We saw that with arctangent. Arctangent of x over x as x goes to infinity. Arctangent of x just wobbles around between negative pi over 2 and pi over 2. But if the denominator is x, that x is getting larger and larger and larger and larger. Denominator is dominating the numerator. The numerator is just flopping around a little bit. Denominator is getting infinitely large. Those fraction values will get arbitrarily close to 0. So that's kind of one of the limits in Calc 1 they call the basic limit. If the denominator goes to infinity and the numerator is constant, then the fractions go to 0. That's one of the 2 basic limits. All right, so here are some sequences. Find the next 2 terms. Find a recurrence relation that generates the sequence. And then find an explicit formula. Okay, so first, obvious part, what are the next 2 terms in this sequence?
14.
14 and 17. So part A, 14 and 17. So we're going along, then we get to 14, then we get to 17, then we get to 20, etc. So this is called an arithmetic sequence. An arithmetic sequence is when we have a common addition to get from one term to the next. That's arithmetic. So we add 3 repeatedly. Anyone know what we do? Well, actually, the next one's an example of it down here. What is, let's just throw up part A here to just, what do you think the next term here is?
2.
2. 1 after that. 1 after that.
Half.
So anyone know what this type of sequence is called? So the first one, we had a common addition to get from one term to the next. The next one, we have a common multiplication. And when you have a common multiplier to get from one term to the next, it's also going to be known as a common ratio. That is a geometric sequence. So geometric is when you have a common multiplier. Arithmetic is when you have a common addition. So that one is a geometric sequence. Okay, so part B says, find a recurrence relation. So recurrence relation is how we get from one term to the next. So we are going to get to, and we have to start somewhere. So I'm going to put a comma over here and say A sub. Now, with recurrence relations, we could call the very first term A sub 1. A lot of times with recurrence relations, you start with A sub 0 as the first term. It does not matter. You can call it A sub 0, you can call it A sub 1. You can call it A sub 10 if you want. It does not matter with a recurrence relation. So we're going to say you have to give it a starting point, though. And then how are we going to get from the prior term? So A sub n plus 1 is the term after A sub n. So there's always going to be a next term that's based on the prior term. So A sub 0 is 2. So I'm going to think of n as being 0 here. So I'm going to find A sub 1 from A sub 0, or I'm finding A sub 2 from A sub 1, however you want to label them, it does not matter. How do we get to the next term from the prior term? Add 3. So we're just going to add 3. So that tells us we're starting at 2. With a recurrence relation, you always have to indicate the starting value. And then this tells us how you bootstrap your way through from one term to the next. We add 3 repeatedly. So that's the recurrence relation. Let's kind of do these two in parallel, simultaneous. So here, A sub n plus 1. Let's see, what are we going to do to the prior term?
Multiply by 1/2.
Multiply by half. So we could write it as n divided by 2. Excuse me, A sub n divided by 2, the prior term. A sub n divided by 2. And we're going to start with A sub 0 equal to 64. So then if we want to get A sub 1, we're going to plug in a 0 for each of those. A sub 0 is 64, divided by 2, we get 32. So that'll get us all the way through. Now let's do this explicitly. So a sub n now we want to build it off of the index, and I started this with 0, so let's finish it with 0. You can start at 1, you can start at 0, does not matter. Any ideas? How can we get to the term value from the index? Anyone see anything?
Can you use sigma notation for this?
Nope. Sigma notation is going to be for when we have a series and we're adding stuff up. We want to create just a function of n. So if we look here, we should be able to do something to the 2 to get to the 8. We should be able to do something to the 3 to get to the 11.
Would it be 3n plus 2?
Let's check. So 3n plus 2. So if we plug in 0, okay, we get to 2. We plug in 1, we get to 5. Plug in 2, we get to 8. So yeah, that's exactly it. 3n plus 2. And so a lot of times, if I'm trying to do these on my own, and I've got some random sequence I want to try to figure out a recurrence relation for, sometimes it's really helpful to set up a little table. And you can take your n values and just do some common things to n. Look at 2n. Look at 3n. Maybe look at n squared. This, just random things that I would think to do. Just some basic mathematical things on n, and just see what happens. See if you can start finding a pattern. And as soon as you find a pattern that works, then, or a pattern that's close, then see if you can do some modification. So if we look at 3n, okay, so 3n, when we plug in 0, those are super close, right? If we look at 0, 3, 6, 9, if we have 0, 3, 6, 9, we notice, oh gosh, they're all off by 2. So it takes trial and error, and we're not going to do a ton of recurrence relations in here. The ones we're going to do are going to be pretty basic, but that's a good strategy. Just sort of create a table, think, and just look for patterns. That's all you can do is look for a pattern. Okay, how about, let's finish this one off. So 3n plus 2. So here, we want to get, and notice that with the formula, well, technically we should tell it when to start. N equals, we're going to start here with 0, 1, 2. But you don't give the initial value. For a recurrence relation, you need to know the actual value that you're going to manipulate. Here, we just need to know the index that we are dealing with. How about that one? Anyone see anything? One thing that should be totally obvious is that those are all powers of 2. So this is a 2 squared, that's 2 to the 3, that's 2 to the 4, that's 2 to the 5, that's 2 to the 6. Okay. Oh, and I put n there. This is an n. This is a sub n, right? This is our value. That's a sub n. I wanted to put a column with n in it. So if n starts at 0, we have that. So anyone see a pattern yet?
2 to the 6 minus n.
So 2 to the 6 minus n. Let's check. So let's just create a column over here that's called 6 minus n. So 6 minus n, that's going to be 6, that's going to be 5, that's going to be 4, that's going to be 3, that's going to be 2. Yeah, now we see that, oh, these all become the powers on 2. Perfect. Yeah. And technically we should sort of say that n is going to start at 0. If you don't say where n starts, you assume it starts at 1. So
Could you also do 32 over n plus 1?
say that again?
Could you also do 32 over n plus 1?
let's see, 32 over n plus 1. Let's see. So if n starts at 0, I don't think so.
Oh, never mind. Yeah, I'm seeing the mistake now.
Yeah, no, because even like if we get to n equals 2, that's not going to be divisible by 3. So yeah, no, that won't work. But a lot of times there are different combinations that will work. So that's and all you can do is try.
The 64 over 2 to the n.
64 over, yes, that works. Because that's the same as this. That is the same as this because we could write this as 2 to the 6 over 2 to the n. All right, that's 2 to the 6 minus n. And 2 to the 6 is 64. So that is an alternative form that you could use. All right. Next one. This one, let's go ahead and do another recurrence relation, but let's start this one at 1 this time, just for the sake of it. Let's suppose we're going to call this the first term instead of the 0th term. Again, it does not matter. You can come up with, if you can come up with the formula when it starts at 0, you can come up with the formula for it to start at 1. It doesn't matter. So here we're going to do that. And any ideas?
36 and then 49.
Oh yeah, for part, oh yeah, we didn't do part A, I guess. Good point.
It's just squaring the n.
So oh no, that's what we're trying to do, the recurrence relation. Oh no, the first thing, did it ask for the next couple terms?
Yeah.
Yeah, okay, yeah, sorry. Okay, so 36 and 49, 64, etc. Okay, so part B is the recurrence relation. Anyone see that yet? So n, we're going to go with 1, 2, 3, 4, 5. We see a bunch of squares in here, so let's just sort of, might as well ask what n squared looks like. That's the thing. Looks like that.
A to the n, a sub n squared.
Say that again.
Would it just be a sub n squared?
So if we're doing the function, but we want to do the recurrence relation, so for example, we want to get to 16 from 9. So if we want to get to 16 from 9, you see what we're going to do? Like, I think what you're saying is a good point because, right, we see that, oh, 3 squared is 9, 4 squared is 16. So a related question would be, if we could get to the index, we just need to add 1 to that index and then square. So how do we get to the index? If we're at 9, how do we get to its index?
Square root of a to the n.
Square root of a sub n. So the square root of a sub n would give us, if we're at 9, would give us 3. Then we want to add 1. That's going to put us at an index value of 4. And then
Square the whole.
square the whole thing. 100%. Very good. Yep. Now, I was writing that chart over there. Usually the chart thing is better for the function piece. So for the function piece, I think it's pretty obvious right now that the term a sub n is nothing more than its index squared.
But we're going to be dealing a lot more with the C kind of thing, right?
Yes.
The explicit.
100%. Yeah. We will be dealing way more with that. Yeah. In fact, we'll only be doing the recurrence stuff just a couple of times down here, and then we'll kind of be done with it after this section. Occasionally it will come up, but not much.
Does this sequence have a special name like the last two?
I mean, this is just the sum of n squared, so it doesn't have a special name, though.
Oh, it's not like an arithmetic sequence.
No. Yeah, this is the sum of, or it's not even a sum, though. Yeah, it's just the sequence n squared. So you would just write it like this. And again, if you just see this and you don't see any index thing, you assume n starts at 1. If you wanted n to start at 0, we would have to sort of indicate that. But yeah.
Do you know, does Pearson ace of 1 or ace of 0?
It will tell you. You'll see that when you're dealing with geometric, starting at 0 makes more sense. And when you're starting with other sequences, 1 usually makes more sense. But we'll see a bunch of examples. They'll usually make it pretty clear. Usually. Not always. Okay, so let's find some limits. So limit of this sequence. And in Calculus 1, you would have called these limits ad infinity. You know, so if you're graphing something and you want to know the end behavior, you take a limit at infinity. Same idea here. Sequences, we don't care what, the sequences start at n equals 0 or n equals 1. There's nothing to the left of the y-axis. So when we say limit at infinity, we literally mean plus infinity. We're not going to minus infinity. How about this limit here? The limit of a sub n is infinity. So 10 raised to the n, as n is getting larger. So we think about n starting at 1, 10, minus 1 is 9. N goes to 2, we get 100 minus 1, 99. N goes to 3, we get 1,000 minus 1, 999. So if we were to write out the terms of this sequence, the terms of this sequence start with 9. And then when n is 2, we get to 99. And then when n is 3, we get to 999, etc. And so it becomes pretty obvious that the limit is infinity, that those are getting arbitrarily large. And hopefully you sort of know this geometric fact. If you take a base and you raise it to a power, if that base is bigger than 1, right, you're multiplying a number bigger than 1 by itself repeatedly, 2 times 2 times 2, you're going to get infinitely large. But if the base is smaller than 1 in magnitude, it gets closer to 0, yeah. Infinitesimally close to 0, arbitrarily close to 0, smaller and smaller and smaller, right? So that's a geometric type of argument that you'll have to make lots of times. Okay, here's another one. So these are some basic limits, right? As n goes to infinity, this exponent is going to infinity. And like we just said, if the base is bigger than 1 and the exponent's going to infinity, that value is going to infinity. If the exponent's going to infinity and the base is smaller than 1 in magnitude, then it's going to 0. So those two basic limits.
Does 1 to the n converge or diverge?
Does this sequence 1 to the n converge or diverge?
Yeah.
What are the terms of this sequence?
Just 1.
So it's 1 repeated again and again and again and again. So are those terms getting arbitrarily close to any one number?
1.
1. Yes. The limit of this sequence, the limit of 1 to the n as n goes to infinity, is 1. So the limit of a constant sequence is itself. Limit of a constant sequence is itself. So it's just like the limit of a constant function. If you were to graph the function y equals 1, the limit as n or x goes to infinity is going to be 1. How about the limit here? So here I set up a little table feature in Desmos. When n is 1, we get 0.9. When n is 2, we get 0.99. When n is 3, we get 0.999, etc. The limit is 1. So let's look and make sure that we can do this algebraically. Let me just move these things down a little bit. So if we are taking the limit of 1 minus, I'm going to write this 1 over 10 to the n. It's usually a little bit easier if you have no negative exponents. Usually most of us can visualize what's happening more easily. So this is one of those basic limits. The top is 1, the numerator is 1, and the denominator 10 to the n, as n gets larger, that denominator gets larger, so those fractions are going towards 0. So we have the limit of 1, which is 1, the limit of this, which is 0, so the overall limit is 1. Make sense?
So we don't need to prove these limits with like integrating or anything, right?
No, we assume basic limits in here. So 1 over a denominator that's increasing without bound is going to go to 0. And the limit of n as n goes to infinity is infinity. So we assume those basic limits, and everything else can be predicated on those two basic limits. All right, so here is a recurrence relation. A sub n plus 1 is equal to 10 over a sub n, and we're going to start at 1. So again, in Desmos, I just created sequence of values. So let's maybe write them out more conventionally with sequence notation. So we're starting at 1, and then a sub 2 is going to be 10. A sub 3 is going to be 1. A sub 4 is going to be 10. And then 1, and then 10, etc. Does that sequence have a limit? Anna?
No.
No. Right? That sequence does not get arbitrarily close to a single number. So for a limit to exist, the terms have to get arbitrarily close to a single number. That's not happening here. It's oscillating. You could say that there is a subsequence that approaches, that has a limit of 1. There is a subsequence that has a limit of 10. But this overall sequence has no limit, which means the sequence diverges. So any sequence that does not converge diverges. If it doesn't converge, it diverges. That's the definition of diverge. If it doesn't converge, it diverges. It has to do one or the other. If it doesn't converge, then it diverges. There is no single number that these terms are getting closer and closer to. All right, now, recurrence sequences are a little finicky. Like this diverging, this is pretty obvious, okay? When a recurrence relation converges, we have a clever algebraic technique that we can use. But it's only if the sequence converges. So if the sequence converges, you need to know what does it converge to. And if you are reasonably assured that your recurrence relation converges, you can do what I'm about to do. So if we look at Desmos, we see, oh gosh, all these term values are the same. So the limit of this certainly appears to be 2. But there's no telling that these 2's actually continue on and on and on. This is some empirical data that leads us to believe the limit is 2. But if you've ever seen that 3 blue, 1 brown video on the digits of pi, you can have something that holds true for like 100 times, and then all of a sudden it changes. So there's no, this doesn't prove that the limit is 2. We strongly suspect that the limit is 2. And here's what we can do. So if we assume that the limit of a sub n does exist, we'll call it L, then we're going to do some clever arithmetic here, clever algebra. So we're going to assume it exists. Why are we assuming that? Because we've looked at empirical data and it certainly appears to be true. And so as long as this is true, that it does converge to L, then we can do the following. So let me first talk about this. If the limit of a sub n is L, then the limit of a sub n plus 1 is also L. Those are two different, you can think of them as distinct sequences. You can think of a sub n plus 1 as its own sequence And if n starts at 0, this sequence is going to start with the sequence just a sub n plus 1. That's going to start with index values of 1, 2, 3, 4, 5. Whereas this sequence a sub n is going to start with index values of 0, 1, 2, 3, 4, 5. So if you think of these, so if you see this, that sequence is going to have n values that go from 0 to infinity, because we were told that a starts at a sub 0. This sequence here, if you think of it as sequence all by itself, if n starts at 0, goes to infinity, isn't the first term here a sub 1? So this sequence has one less term than that sequence. So you can think of each of these as individual sequences. This has one extra term, but we all know that when you're taking a limit at infinity, what happens in the beginning is meaningless. It's what happens out there, right? If you're doing a limit at infinity, if you're looking at n behavior, you're talking about n going to infinity. It doesn't matter when n is 0 or 1 or 2. We're talking about when n is 10 million, 100 million, a billion, right? We're way out there. So these two sequences, you can think of them as distinct sequences. This one has one fewer terms, but their tails, the terms out at the end, are the same. And their limits will be the same. So here's what we do. So that's the backdrop. We assume that a sub n has a limit of L, which means if you treat a sub n plus 1 as a distinct sequence, its limit is also L. And so the idea is that you're going to take this recursive expression right here, this recursive equation, and you are going to take the limit of both sides. So we're going to apply the limit to the left and apply the limit to the right as n goes to infinity. Well, the limit of a sub n plus 1 is L. The limit on the right, the limit of a constant is itself. The limit of a sub n is L, and you get this algebraic equation. So we're going to treat each of these as individual sequences. We take their limits. We get this. Multiply everything by 2 just to clear out the fraction. I guess it's simpler than that. If we subtract L over 2, don't we get L over 2? And so then multiply both sides by 2. That tells us what the limit is. So if you have a recursive sequence that converges, you can find what it converges to with this process. It only works if the sequence converges, though. If a sequence diverges, a recursive sequence diverges, you need to look at that. This technique only works if it converges. Ari?
Wouldn't it be easier to just convert it to an explicit formula?
You can't always do that. So this one, this one is kind of weird because it's a constant sequence. So its explicit formula would be 2. It would be 2 with braces around it. But if you can, yes.
So this formula, is there any way where it proves that it's not the limit that you thought it was?
So potentially.
Okay.
Potentially. If the sequence does converge, this will find the limit.
Okay.
99% of the time when you're looking at your empirical data, it's going to line up.
It's going to. Okay.
Yeah.
All right.
Does the fact that A naught being 2, does that make the rest of the series 2?
The rest of the
I feel like I'm missing
sequence?
something. Yeah.
So the first sequence is the one that's a sub n. That one is, both sequences are 2, 2, 2, 2, 2. But the index value for this sequence here starts at 0, whereas the index value for this one starts at 1. Because if n is going to start at 0, then this sequence right here has initial value of a sub 0. This one, if n starts at 0, it has initial value of a sub 1. So it has one fewer terms.
But you set the sequence equal to 2.
We did not set the sequence equal to 2. So we took the formula for the sequence and we took the limit of both sides. So here is the original formula. We take the limit of both sides, and the limit of the left side is L, the limit of the right side is 1 plus L over 2.
Oh, so we had to prove that A0 was 2 then?
No, we're given that A0 is 2. We're trying to prove what the limit is. So when we look here, it's like, oh yeah, the limit appears to be 2 because all the term values appear to be 2. We'll do a couple more. We'll do a couple more. So let's do a brief overview of what a series is. Just like sequences, when you're in calculus and someone says series, it means infinite series. We don't want to have to say infinite series every single time. So if you hear the word series, it means infinite series. If the series is finite, that's when we're more explicit. And we're going to say the finite series from n equals 1 to 10 or whatever. So if you just hear the word series, always assume that it's infinite, that it goes on forever and ever. So here's our notation. We're starting with a sequence of terms. So here's our sequence of terms. But instead of just listing the sequence of terms, we're going to add them together. So if you start with the sequence of terms and you decide you want to add them all up, this is our notation. So that's capital sigma. Capital sigma, Greek letter S, S for sum. Right, we're summing them up. So that's an infinite series. Right there. We're adding an infinite collection of terms together. Could be positive, could be negative, who knows? There's just an infinite collection. We need a mathematical way to decide whether this infinite sum is finite or not. If the series turns out to be finite, we say that the series converges. If the series does not converge, it diverges. Does one or the other. So if the series converges, it's equal to a number. If the series diverges, it could be equal to infinity, it could be equal to negative infinity, a million things could happen. So if it doesn't converge, it diverges. But there's lots of ways divergence can look. It can diverge by oscillation, it can diverge in lots of ways.
Immediately I'm thinking, would no arithmetic sequence converge?
Yes. No arithmetic series will converge. Because those terms are getting bigger and bigger and bigger, right? Because you could do subtraction. And let's just think positive, though. So if you're adding some number again and again and again and again and again, and then you're adding all those terms together, yes, it's going to go to infinity. So an arithmetic series will diverge. Geometric series are the ones that we're going to be more interested in. So now we need a mathematical way to get at whether this series converges or not. We know how to take limits of sequences. Taking limits of sequences is identical to taking limits of functions, which you did in Calc 1 and we've done in here. So a sequence is a function. You know how to take limits of sequences. You know how to take limits of functions. We want to turn this problem into a limit problem. And so what we do is create a new sequence called the sequence of partial sums. So we want to build a secondary sequence that is called the sequence of partial sums. Okay? So here is our new sequence. First term of the S sequence is the same as the first term of the A sequence. But what we are going to do is bootstrap our way through, and we're going to keep adding one more term. So S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms. So we have now created this new sequence that looks like this, with S notation. So if our series converges, these S's are getting arbitrarily close to whatever S is. Usually, we are going to say that the limit of S sub n is, or L. Here they use L. You can use S or L. So if this converges, these S's are getting closer and closer to, in this case, they call it L. So whatever that series converges to, if it converges, this sequence of partial sums is a sequence that converges to that value. And so a really good example, let's just come down here for a second. If we think about something like 0.3 repeating. So if we have this sequence of terms which we turn into a series, we know that this is going to converge to 1/3. So the sequence of partial sums looks like this. So the sequence of partial sums is going to be this sequence that is getting closer and closer to L, which in this case is 1/3. So the sequence of partial sums creeps up slowly to whatever that limit is. Harrison?
So when you get to this S like thing, this is where you find out if S converges or diverges.
Yep.
Okay, so S can either converge or diverge.
Yep.
Okay.
So this sequence, the S sub n sequence, converges or diverges. If the S sequence converges, then we say that the sum of the series is L. Whatever that sequence converges to, if we call it L, then we say multiple things. We say the S sub n sequence converges to L. We say that the A sub k series converges to L. We say that the sum of the series is L. Like, there's a lot of things that we can say that all mean the same thing. So if we build this sequence, the S sub n sequence, we find its limit. If that limit exists, then the series converges to that number. Sometimes we just say that it equals that number. And if that sequence diverges, we say the series diverges. So the only way a series converges is if this is true right there. If S sub n sequence converges to L.
So how is this actually used in the real world?
We'll get there. We have a long way to go before we can talk about those questions. We'll get there, though. Although I can give you one simple example, I guess.
Approximating.
Calculators. This is how calculators do their math. Like if you type into your calculator e squared, how do you think it does e squared? Well, what it does, you're going to see in this section we're dealing with just numbers. In the next chapter we're going to deal with infinite series of functions. So we're going to have like x plus x squared plus x cubed plus x to the fourth plus x. We're going to have infinite polynomials. And calculators, mechanical computers and things, they can do addition, multiplication, and division really easily. And so what we do is take like e squared. We're going to create an infinite series for e to the x. We're going to replace the x with a 2. And then we're going to have an error calculation based on the width of your calculator's screen. And it's going to go out. There's a mathematical formula that tells you what the error is. And if we want to have it accurate to 9 decimal places or 9 values on your screen, then the calculator figures out, okay, I've got to go to this infinite series, and I've got to go out to 100 terms, and then it will do it.
I'm sorry I asked.
Right. Every calculation you do on your calculator with a cosine or a sine, it's dealing with an infinite series that's terminated, so it's really a finite series. But it's using the concept of infinite series with an error approximation so that it's accurate for as many digits as you can see. So every single day when you type into your calculator, you're using series.
What's the point of introducing a series if we're just going to immediately change it back into a sequence?
It's not exactly what you just said. we know how to apply limits to sequences because sequences are functions. So we're trying to take this new object called a series and apply what we already know. So we already know how to take limits. We've already done limits all through Calc 1 into Calc 2. So we know how limits work. So the idea is that if we can rewrite this series in a way that we can use tools that we already know, then we can analyze whether the series converges or diverges. So if we can turn the series into a sequence and then take the limit of that sequence, then we have a tactic to get to the limit of the series, or the sum of the series. Now, this all looks pretty easy, right? Oh, just take S sub n and take the limit. Finding S sub n? That's like going out to, a golf course or a disc golf course and throwing an ace or hitting an ace or, throwing the coin into the bottle from far away. Finding S sub n is very, very difficult, if not impossible. So, when we can find S sub n, it's actually really easy. Most of the time, truth be told, is that we can't find S sub n, which is why we have this horrible thing. If we go to our handouts, that is why we have this horrible page here with all these tests. These tests all are a result of the fact that you can't usually find S sub n. So then we need another way to decide if a series converges or diverges. So if we can find S sub n, we just take the limit of it, but most of the time you can't, which is where all these series tests are going to come in.
This is where people screw up.
Yeah.
To remember all the tests.
Remember all the tests and when to use them and how to use them.
I was just about to ask if we had to memorize them.
Yeah, you need to know those.
What's an example where you can't do this?
What if you gave me?
Oh, we'll get to one soon. Yeah, we'll get to one soon. I'll show you. 99% of the series we look at, there's no S sub n. Okay, so let's look at these guys. No, let's take a break. Let's take a 10-minute break. Then we'll do some more examples. We'll do some examples. And I think somebody came in. I did not give a test back to, I believe. Pause.
Time for S sub n.
S sub n.
I feel like that thing's gonna start popping up in our nightmares.
S sub n?
Yeah.
It might.
Yeah, I guess I didn't think.
Okay, so we all know what this series converges to. What does this series converge to?
2/3.
2/3. So we all know that. So it converges to 2/3. So we know that. And you should be able to, I don't know, they used to teach us in
I started that.
algebra. I don't know if they still do. Do you know how to do this algebraically? We are going to learn that this is a geometric series and learn how to do it with series techniques. Do you know how to do it algebraically? I can't remember.
You showed it once.
Did I show you? I feel like I have this memory of doing it. So
Yeah, you showed us with like 109, I think.
yeah. So it's that idea. So, okay. So if we let x equal 0.6 repeating, then we multiply both sides by 10. That moves the decimal one place over. Then on the right, we can separate this into x plus 6. Right? The decimal point we can break apart. That's 6 plus the decimal part. The decimal part is x. So now we have 10x, subtract x, we get 9x equals 6. So here's how you can do it algebraically, which of course is helpful. But we'll learn how to do it very soon, how to do it with a geometric series. Okay, so this just says, for the following series, find the first 4 terms of the sequence of partial sums and then make a conjecture about whether it converges or diverges. So the sequence of partial sums, the first term always matches the first term of the A's. And then we do the first two terms next, so this is going to be 0.66, and then 0.666, 0.6666, etc. And pretty obvious that the limit of S sub n is going to be 2/3. So our conjecture is that yes, it converges. We haven't proved it with series yet. We did prove it algebraically, but we will prove it with series in the near future. So same idea down here. The S sub n series starts with the first term, and then the sum of the first two terms, and then the sum of the first three terms, and then the sum of the first four terms. And what do you think this converges to?
5.
Perfect. So the limit of S sub n as n goes to infinity will be 5. So that is the idea. One more slide in our overview section. Okay, so I mentioned a few minutes ago that formulas for S sub n are often hard, if not impossible to find. Here's one that's not so hard to give you a flavor of it. So we're going to look at this sequence, this series right here. The terms in this series, we start at 1. So we plug in 1 and we get a half. Plug in 2 and get a fourth. Plug in 3, get an eighth, etc. So that is our infinite series. This is a geometric infinite series. What is the common multiplier?
2. Well, 1/2.
1/2. So 1/2 is the common multiplier. So we do repeated multiplication by 1/2. Right? So this is a geometric sequence right there. Now the sequence of partial sums, let's see, what did it say? Find the first 4 partial sums. Okay, so the first partial sum, 1/2, just match the first term. And then we get the next 2 terms added together. Then we get the next 3, then we get the next 4. And now we want S sub n. So let's see, can we see a pattern here that allows us to build S sub n? So let's focus on the index and on the denominator over there. And what is the formula that gives us that denominator based on that index?
Quick question, that means that S of n is the sequence with S of 1, comma, S of 2, comma, S of 3?
Mm-hmm. Yes. So how do we, so these are the values in the S of n sequence. So we're trying to come up with an explicit formula to grab each of those values. So what is the denominator? 2 to the n. 2 to the n. So, right? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So in general, 2 to the n. And what is the numerator? 2 to the n minus 1. So here we have done it. We've come up with an explicit formula that represents the nth term in the S sub n sequence. So there it is. That is, and again, this one's a pretty easy one. This one's a very easy one. It's usually much harder than this to find S sub n, often impossible. But if S sub n can be found, computing the limit and finding the sum of the series is typically straightforward. So now we want to take the limit of S sub n. So the limit of S sub n as n goes to infinity. Well, let's see. We're going to have to use a technique here to do this. There's a couple ways to do it. What is that limit going to equal?
Indeterminate form.
I think I heard it. Did you say 1? Answer is 1. Couple ways that we can get to it. So there is the technique of splitting the fraction. That certainly works. This is 1 minus 1 over 2 to the n, which is probably the way most people would approach it. If you have a denominator that's one term, you can share it with the numerator. And then the limit of this, as n is going to infinity, the limit of 1 is 1. Limit of a constant is itself. And then this fraction here, that's going off to 0. Because we have a constant numerator, denominator is getting infinitely large, so the fractions are getting infinitesimally small. So that is our limit. So then we can say a whole bunch of things. So the sequence of partial sums converges to 1. You can say the series converges to 1. You can also say the series is equal to 1. The value of the series is 1. So you can say all those things. You can say this whole thing equals 1. There's lots of ways to say it. Sequence is 1. The value of the series is 1. Let me back up. I just said the limit of S sub n sequence is 1, not the limit of A sub n. Can somebody tell us what the limit of the A sub n sequence is? 0. Right? These are going to 0. The A sub n sequence is going to 0. Oh, and I have k's and n's. So whether you use a k or an n, obviously it doesn't matter. Some books use an n, some books use a k. Technically, I probably should put a k there. Is it clear that this limit is 0? What do you think? For a series to converge, is it possible that the limit of A sub n is not 0? If the let's suppose the
Depends
limit of
on
A
what
sub n is
Depends on what the denominator in the, I want to say the summand.
summand is right.
Okay.
If that limit is not 0, the series diverges. If the limit of A sub k or A sub n, whatever you want to call it, let's suppose it's 0.1. That means out in the tail of the series, it's as if you were adding 0.1 to itself a bazillion times, which is going to diverge. If you add any positive number to itself an infinite number of times, you're going to infinity. So one necessary condition is that the terms have to go to 0. It's identical to improper integration. Remember when we were doing improper integration, right? We had the ski slope. If we didn't have a limit of 0, we knew that the area beneath the curve was infinite. The limit had to be 0 first and foremost, but then it had to go to 0 fast with improper integration. Same idea here. The only way you can get an infinite series to converge is the terms have to go to 0 first and foremost. If they don't go to 0, there's no chance that you have a finite sum, that the series is finite. Okay, so the terms have to go to 0, but then they have to go to 0 fast also.
So, I'm just like thinking about it. If
Yeah.
you find out that the sequence does not go to 0, then you know that it's divergent.
You know the series is divergent.
Okay, and then are there some cases where it does go to 0, but it still diverges?
Yes.
Okay.
So that classic one is the harmonic series,
All right.
which actually I think we're going to do in a minute.
Okay.
Well, let me just put it up here. So the harmonic series, so if k goes from 1 to infinity, 1 over k, this is 1 plus 1/2 plus 1/3. So we've already seen this with improper integration. We
Yeah.
showed that the integral of 1 over x from 1 to infinity was infinite, and that's true here too. So these terms are going to 0, they're just not going to 0 fast enough. So it's necessary that they go to 0, but it's not sufficient. It's not enough. They have to be going to 0 fast. So that series will diverge. That's the harmonic series.
What about 1 over k to the negative 1?
1 over k to the negative 1 is k. And what does that go to?
Minus a 12.
OMG.
The second I
Where
heard-
is my chalk when I need it?
The second I heard that, I was like,
Yeah.
I wonder.
Oh, yeah.
Yeah. It's not negative 12. Unless you've got a screw loose. Okay. So, all right, that's the overview of sequences and series. Now we're going to get into details of sequences, and then in the near future, details of series. So let's go to sequences. So first theorem, if you have a sequence that is defined explicitly, so it's a function, and then you find the limit of the, for lack of a better reason, well, it's not really a parent. It's the continuous function of which the sequence is a subset. You could call it the superset, the continuous superset. So f of x represents continuity. When we use x, we mean x can be any real number, not just positive integers. When we use n, we're indicating that n has to be a positive integer. It can't be 1/2 or a third or pi. So what this is saying is that if we have a sequence and the superset, the continuous function, has a limit, then the sequence has the same limit. So we're trying to find the limit of the red dots, and we know that the limit of this black curve is L, which is 1 in this case. Then the sequence of the red dots is also 1. So if the continuous function that contains the sequence has a limit, then the sequence has the same limit. There's no way those dots can go anywhere else. They can't go somewhere that the function is not going to, the continuous function. All right? They can't pull themselves out of the function. So if the continuous function converges, then the sequence converges to the same thing. Make sense? Intuitively? Right? Sequence has to converge to the same thing.
Does this apply to alternative harmonics as well?
To what?
Alternative harmonics?
Alternating?
Yeah.
Yes. But with alternating. So if we come up with but the one difference is that you need the sequence has to be embedded in a continuous function. So if we can find a continuous function that models the harmonic, the alternating harmonic, then absolutely. Now, off the top of my head, I don't know what that continuous function is. But if we have a continuous function that models the alternating harmonic, then yes, we just take the limit of that continuous function.
Plus or minus 1 over x.
No. Close. So absolute value, maybe? I don't know. We could try to figure it out.
It could be absolute values.
Now, the converse of this is not true. So the converse of this is not true. Everyone understand what the converse is? Converse is going the other direction. So this says if the continuous function converges to L, then the sequence converges to L. The converse would be the sequence converges to L, so the continuous function converges to L. That is false. So for example, if we look at the function right here, so cosine, and we look at this sequence embedded within the cosine curve, so there's cosine, and now we're going to look at this sequence that's embedded within it. There's the sequence. that sequence converges. That sequence is a constant sequence, 1, 1, 1, 1, 1, 1, 1. So this sequence converges to 1, but cosine does not converge. So the theorem is one directional. If the continuous function converges, then the embedded sequence also converges. One direction. If the continuous function converges, then the embedded sequence converges. If an embedded sequence converges, it tells us nothing about the continuous function. Fair enough? All right, limit rules. So all of the intuitive limit rules that you use for continuous functions, they apply for sequences. So we've got two sequences that converge to A and B. If you add two sequences together, the adding or the subtracting of two convergent sequences will be A plus or minus B. So all this intuitive stuff that you've also seen with functions. If function f converges to L and function g converges to m, then the sum of them converges to L plus m. All that stuff you did in Calc 1. All those limit rules apply. If you have a constant times a function, you can factor the constant out. The limit of the function is a, so the limit of the overall product is c times a. So all those intuitive things. Constants can factor in and out of limit, just like they did in Calc 1. Constants can factor in and out of derivatives, out of integrals.
Is there anything that they can't factor out of?
Constants, no. Constants can always factor out. So limit, if we have two sequences and we multiply them together, as long as both of those are convergent sequences, the limit of the product is the product of the limits. Same for the quotient. The limit of a quotient is a quotient of limits, as long as the denominator is not 0. As long as that's true, then no problem. So all those basic limit rules apply. Now, down here, super important, I think you kind of get it. When you're looking at a sequence that goes on forever and ever and ever, you can chop off the head of the sequence and it tells you nothing. That doesn't change whether the sequence converges or not. Right? The sequence converging is all about what's happening out at the tail. You can chop off the first 1,000 terms, the first 1,000,000 terms. That does not affect whether the sequence converges or diverges. Right? It's the tail. It's what's going on out near infinity. And when you go way, way, way out there. So when we talk about convergence of a sequence, we are thinking about what's going on in the tail, not the front of the sequence, not the head of the sequence, but the tail out there. So you can chop off as many terms as you want. So in other words, you can have a sequence that does all sorts of weird oscillation, but if it eventually settles down, and it can converge. Like the first 1,000 terms don't matter. All right, so let's find some limits. So these are sequences. And you learned a bunch of weird techniques in Calc 1 that we're going to use here.
Is it true that the index of every single sequence goes up by 1?
Yes. Yeah. So sequence is always a function of the positive integers. So, yeah. So, we want to find the limit of this. And the limit of this, one technique you learned in Calc 1 was to divide by, depends on who you talk to, the highest power of n in the denominator, whatever. One of those two techniques. Hopefully everybody understands that dividing everything through by some expression is the same thing as multiplying by 1. If you divide the numerator by n to the 12, and you divide the denominator by n to the 12, what you've really done is just multiplied by 1, and you have not changed the value of anything, you've just changed the look. So I divided everything by n to the 12. If you divide all three of these things by n to the 12, you've really just multiplied by 1. right? If you have the numerator over the denominator, if you multiply the top by whatever, let's say that, if you divide the numerator by n to the 12th, and you divide the denominator by n to the 12th, you've just multiplied by 1. So if you divide every term by the same expression, you've multiplied by 1, it's equivalent. If you multiply every term in the expression by the same, if you multiply every term in here by the same expression, you've multiplied by 1. So that's going to be a common technique. And now when we take the limit, where does this one go to here? 4 over n to the 12th goes to, yeah, that goes to 0. Yeah, so I don't want to, well, I guess it doesn't matter. Okay. So what is the overall limit? 1/3. So everybody familiar with that technique? Divide by highest power technique?
Now I am.
There is another, what's that?
Now I am.
Uh-oh. There is another technique called L'Hopital's rule. Has anyone not heard of L'Hopital's rule? Anyone? L'Hopital's rule says if you have an indeterminate form, infinity over infinity, 0 over 0, you can take repeated derivatives until you get to a limit that you can evaluate. So that idea is pretty intuitive. We've got two functions and a fraction. The best approximation, if you f over g, f prime is the best approximation for f, best linear approximation. G prime is the best approximation for g. So if f over g is approaching something, its derivative over derivative should be approaching the same thing. So if you take the best approximation for the top and the best approximation for the bottom, that quotient should approach the same value that f over g approaches.
Does this sequence start at 0 or 1?
Can't start at 0. The second one?
No, this first one.
Doesn't matter. Doesn't matter. As long like this one can't start at 0 because we'd have division by 0. So
You just have to logic your way through
because
that.
like I said a few minutes ago, it doesn't matter if you chop off the first 1,000. You can start at 5 million if you wanted to. Whether it starts at 5 million, 0, or 3, the limit is the same. The limit depends on what's going on way out in the tail. So it doesn't matter where it starts. Okay, let's look at this next one. So with this next one, we have the same idea. When you have polynomial type expressions, you can divide by powers. And it doesn't really matter what you divide by. Some books divide by just the highest power of n. Some divide by the highest power of n in the denominator. It doesn't matter. You will get there one way or another. So this limit, as n goes to infinity, let's divide by, I'll show you the difference. So if we divide everything by n to the 5th, we're going to have 1 plus 3 over n to the 4th. That's the numerator. So dividing everything by n to the 5th. So we're dividing the numerator by n to the 5th, and we're dividing the denominator by n to the 5th. So then we're going to have 10 over n squared. We're going to have 1 over n to the 4th. Look at that. Everyone okay up to that moment? Can I set the opacity? So where do these all go?
0, 0.
I guess if I circle them, I don't obscure them. All right.
So just 1.
Undefined.
So is the denominator got a consistent sign, SIGN? Denominator is always positive or negative? Positive. This is what's important when you're dividing by 0. You need to know, are you approaching 0 from the right or from the left? This denominator is always positive, so this denominator is going to 0 through positive values. So we have 1 divided by something that's going to 0 through positive values, so it goes to plus infinity, not negative infinity. Right? So the denominator is going to 0 through positive values, but it's getting smaller. If the denominator is getting closer to 0 and the numerator is constant, we're getting a bigger and bigger quotient. Right? 1 divided by a tenth, 1 divided by 100th, 1 divided by 1,000. We're getting a larger quotient. But it's always positive. So this will go to positive infinity. You can also say the sequence diverges. Now here's where we come up to some kind of ripples in the notation. This limit does not exist. Although in calculus we always write the limit of this sequence or this function equals infinity, that's kind of a little bit sloppy because this limit does not exist. Even though we say the limit is infinity, that limit doesn't exist. What we're doing is describing how it does not exist. So this is also correct to say it does not exist. That is correct. But it's not as correct because we don't know how it doesn't exist. Right? So this doesn't exist because the values are getting closer and closer to infinity. The definition of a limit existing is that you get closer and closer to a number. Infinity is not a number. So this limit doesn't exist, but we can often indicate why it doesn't exist. And so better than D and E, we say it goes to infinity, then you're envisioning the values are getting bigger and bigger and bigger as it goes to infinity. But just be clear that this limit does not exist, even though we say the limit is infinity. It's just kind of shorthand math to say that. How about this sequence? So this sequence, the limit of this sequence, so we're going to use, when we see an n, we're talking about a sequence. This sequence is embedded into this continuous function. When we use an x, we're thinking of the continuous function arctan of x. So when we're thinking about what's going on here, this is what we should have in our mind. Arctan of x looks like that. And we don't care about what's happening to the left. So there's arctan of x. And here is our sequence, which is embedded within it. So the sequence is embedded within the continuous function. And the continuous function has a limit of pi over 2. So the embedded sequence must have a limit of pi over 2 also. So if the continuous function converges to a number, any embedded sequence converges to that same number. There. All right. Log limit process, something you learned in Calc 1 also.
Oh no, not this stupid. I hated this so much.
Oh, I wish I had chalk.
What for? Oh.
Projectile motion.
That was my engineering professor at school.
There's Sexwell markers around.
He had a little clay shooting ball.
Wait, dude, I like that idea. It was in this classroom, it was like 10 years ago, we were always back in rows back then. And there was some kid that's sitting right where Caitlin's sitting that was always talking. And I asked that person multiple times to stop talking, and they just were always talking loud. And I took a marker. I took one of these dry erase markers, and he had his water bottle it was just sitting in front of him, and it was open, and I was standing right here, and I just lost my patience. I just whipped my marker. It pegged his water bottle perfectly, tipped and spilled water all over him. It was classic. It's like so fun. So that, you know, we used to throw chalk, but chalk is, you know, it's tiny. A marker, though, that can do some damage. If you've got an open water bottle. Oh, I'm trying to remember what that kid's name was. He was very silent the rest of the semester.
Gee, I wonder why.
I wonder why. All right, so the limit as n goes to infinity of this whole expression. Now, this is an indeterminate form. So in Calc 1, you sort of talked about all those indeterminate forms. Here is one of those indeterminate forms, 1 to infinity.
Is that infinity over infinity? Oh, never mind.
Right? If you were to take the limit and push it inside, the limit of you know, these cancel, right? And so the limit of this is 1. What's that look for? With a scrunchy face is not just looking. So, if you were to do long division here, you could do long division if you wanted, but this limit's going to be 1 inside. You could do L'Hopital's rule, the derivative of n is 1, the derivative of n plus 5 is 1, 1 over 1 is 1. So this is going to be the indeterminate form, 1 to infinity. The exponent is going to infinity. And limits of that form can go to anything. And so we don't know that we have to do something in order to figure out what this limit is. What is the classic limit, the most important limit of them all, that's of this form? That many of you should have indirectly seen in college algebra with graphical techniques. There is a really famous expression, 1 plus 1 over n to the n. What does that go to? So this is 1 to infinity, right? Indeterminate form, 1 to infinity. And what does that go to? It's related to compound interest. Goes to E. Right? So you should have first seen that in college algebra, where they did it just graphically. And this is a really interesting thing, because we've talked about this geometric principle earlier. Negative 9 raised to the nth power goes to negative 9 to the x to n goes to 0.9 times 0.9 is 0.8, 1. It's going to go to, if you take a number less than 1 and multiply it by itself repeatedly, you go to, ooh, yeah, that's a 0. It goes to 0. If you take a number bigger than 1 and multiply it by itself repeatedly, it goes to infinity. So this is what's very curious about this. This base is always bigger than 1, right? 1 plus 1 over n is always bigger than 1, but it's not a constant, right? It's the base in here is getting closer and closer to 1. The exponent is going to infinity. So most students' instinct when they see this is like, oh, that's always bigger than 1, so if we raise that to the nth power, that should go to infinity. The fascinating thing about this is that, yes, this is always bigger than 1, but it's approaching 1 fast enough that the exponent doesn't win and take it off to infinity. This goes to E. So we'll look at this a little bit later, but how do you prove it? You prove it with the log limit properties. But that's a super fascinating limit, because limits of this form, 1 to infinity, can feel a little strange. So how do we do it? How do we take that limit? So you learn the log limit process, and the log limit process says this. What we are going to do is, first, we are going to convert things to x's, because we are going to have to take a derivative at some point. And so usually, you don't have to. It's fine if you don't want to convert to x's. But if you think about x's as coming from the continuous realm and n's coming from the discrete realm, and you have to take a derivative or something.
What did I do?
You're the type that's not going to want to switch it to x.
I do switch to X. I hate other numbers.
Oh, these are called letters.
Well, listen, I was looking at a number at the time.
Whatever he looks at. So we take the natural log of both sides. And the reason we take the natural log of both sides is that now the exponent can float down in front. So
I specifically took the time.
it's at this stage that we're going to take the derivative of both sides with respect to x.
I don't want to work with letter H or something.
So what is the derivative of the left side with respect to x?
dx.
I've heard some close things.
Y over Y.
So the derivative of a log is 1 over the inside no matter what, times the derivative of the inside, the derivative of y is y prime. So we would write this as 1 over y times y prime. So we're thinking about y as a function. Y is a function of x. So 1 over y times y prime.
I said dy over Y.
And then
It's hard.
how do we differentiate the right-hand side? What rule would we need to use? Product rule, because we have a product,
And product.
right? So product rule, we've got the x, and then we've got the log function. So we're going to use the product rule. So the product rule says, first, multiplied by the derivative of the second. Derivative of the second is 1 over the inside. So 1 over the inside flips the inside. Multiplied by the derivative of the inside, which is a quotient. So we have to use the quotient rule. So first derivative, second, right? We're differentiating the second. It's 1 over the inside times the derivative of the inside, which is low function times the derivative of the upper function, low d high, minus high d low over low squared. So that's the first part of the product rule. First function, derivative of second function is 1 over the inside times the derivative of the inside plus the derivative of the first function multiplied by the second function. Everyone okay with that? Product rule? Any question on that? Question?
Why would you have to use, I mean, I guess I can see, but why would you have to use the quotient rule when you're, is it just because when you're multiplying by the derivative, you have to work
Oh,
out?
you know what I just realized? Should I be taking a derivative or a limit? We started talking about, I was helping someone in the Math Center earlier today in Calc 1, and we were doing log differentiation, not log limit. And so in my mind, I was taking a derivative instead of a limit.
Confused for a second.
We shouldn't be doing a derivative. We shouldn't be doing a derivative. We should be doing a limit. My bad.
So lost.
My bad.
Regardless of that.
But this should not be hard though for you. If we were taking a derivative, is there part of this derivative that's, because you will have to do this for derivatives.
What's weird about it is how it's, when you're taking natural log of x over x plus 5, why you're using the quotient rule. I mean,
Because this is a quotient.
Well, yeah, because.
It's also chain.
Yeah, it's chain rule, quotient rule, product rule all together.
Because when you're multiplying it by the derivative of x, you have to.
The derivative of the
incorporate-
inside.
Yeah, well, yeah, but you have to incorporate the quotient rule because it's the derivative of the inside.
Yes.
Okay.
So do we have to convert to x or not?
Yes. But,
I mean, you don't have to.
yeah.
Oh my
But
god.
we should be taking limit right here instead of derivative. So let's
See, I
do,
use sigmas as a thing.
so we're gonna take limit right here, not derivative. Derivatives are so fun, but we're not gonna have that kind of fun right now. So we're gonna take limit. So first we use x, now we do limit. So then we take limit of both sides, not the derivative.
Right next to
Not
us.
sure why I was thinking to take derivatives. All you people that read ahead should have stopped me. Okay, so limit, not derivative, because that's what we're trying to find. Calc 1, you do that log differentiation. Here we're doing log limit.
As x or y goes to what?
X is going to where? We're taking limits at infinity. So limit as x goes to infinity. Okay, on the left side, so our whole goal is to find the limit of y. Right, here's our y, we want the limit of y. Let's see. So we're going to push the limit function inside the log function. That can happen because the log is a continuous function. The limit symbol has a lot of superpowers. It can go right through continuous functions. Very powerful, this limit symbol, this thing we call the limit. On the right, this limit here, what we want to do is create a limit that is in an indeterminate form that we can evaluate. This is in an indeterminate form. This limit here, tell me what the two, so what does x go to as x goes to infinity?
Infinity.
Infinity. What does this go to as x goes to infinity? 1 on the inside, so natural log of 1 is 0. So this is the indeterminate form infinity times 0. Right? It's like an arm wrestle. Is the one going to infinity faster than the one going to 0? We don't know, right? That's indeterminate. And so what we want to do is change this into an indeterminate form that we can use L'Hopital's rule. We would like to change this into the following. We can think of 0 as 1 over infinity, and then we're going to have this indeterminate form infinity over infinity. That's where we want to go. Because if we can get to infinity over infinity, then we can use L'Hopital's rule and take derivatives. That's where we want to take derivatives.
So you're saying that as x goes to infinity inside the natural log, then that's infinity over infinity, which equals 1?
Yes.
Because they're the
Because
same
of
kind of
L'Hopital's
infinity.
rule, they're the same power. Right, L'Hopital's rule says if you want to take the limit of the x over the x plus 5, you take the derivative of the top and get 1. You take the derivative of the bottom, you get 1, and you reevaluate the limit. The limit of 1 is 1. So L'Hopital's rule applies anytime we have an indeterminate form of infinity over infinity or 0 over 0. So now here's how we switch it. So we do what I did right here. I just move one of them into the denominator. If I move the 0 into the denominator, you can just switch it, right? You could turn this into 1 divided by 0 or turn this into 1 over infinity. It doesn't matter. So here's what we usually do is shove the x into the denominator. So if we take that x, what does x become if I push it into the denominator? Multiplication by x is the same as division by 1 over x, right? If you divide by 1 over x, that's the same thing as multiplying by x. Now we have an indeterminate form that is going to be infinity over infinity or 0 over 0. Which one?
0 over 0.
0 over 0. Everyone see it? As x goes to infinity, 1 over x goes to 0. Inside here, you push the limit inside, x over x plus 5. That limit is 1. Natural log of 1 is 0. So now we can use L'Hopital's rule. So L'Hopital's rule, I'll just say L comma H. You can do that, or some people will do this instead. They'll do 0 over 0 like that. Just somehow indicate that you're using L'Hopital's rule. So here's L'Hopital's rule. L'Hopital's rule says that the limit as x goes to infinity, it does not matter whether it's 0 over 0 or infinity over infinity, we now are going to take the derivative of the top and the derivative of the bottom separately, not a quotient. L'Hopital's rule says the fraction approaches the same thing as the fraction of derivatives. The fraction of functions approaches the same thing as the fraction of derivatives. The derivative in the denominator is easier, so let me do that one first. Now in the numerator, the derivative of a log is 1 over the inside, so we flip the inside. 1 over the inside times the derivative of the inside. The inside's a quotient, so we have to use the quotient rule. So it's going to be low d high. I find it easiest to put everything in parentheses helps. So there's low. D high is 1 minus high. D low is 1. We're going to put all of that over low squared, so x plus 5 squared. So there's the quotient rule. Low d high minus high d low over low squared. Okay, now we have to simplify that shenanigans. Okay, so let's simplify this. So this will all be limit. I'm not going to cancel any of the x's out quite yet. Just let's make sure we all see where everything is going. So there's the x plus 5 over x. If you divide by this fraction here, we could make this minus x squared over 1. Right, divide by a fraction, multiply by the reciprocal. Now we've got the bracketed junk. X plus 5 times 1 is x plus 5 minus x. X plus 5 minus x. 5. In its denominator, we have an x plus 5 squared. So this is everything written more compactly. Everyone okay with that?
Where did the 5 come from?
That 5 came from right there. Because this is x plus 5 minus x. X plus 5 minus x is 5. X plus 5 minus x. We have one more big simplification that can occur now. We can cancel out an x plus 5. We can cancel out an x. So we're going to have limit of minus 5x in the numerator divided by x times x. I canceled out that x. I said it, but then I didn't do it. So in the denominator, we just have x plus 5. So I canceled one of the x's out from the x squared. One of the x plus 5's canceled. So we're left with minus 5 times 1x left in the top, and in the denominator, 1x plus 5. And what is that limit equal to?
-5.
So this is, again, L'Hopital's rule. This is indeterminate. This is infinity over infinity. And it doesn't matter if it's negative or positive infinity. L'Hopital's works either case. So if you take the derivative of the numerator and the derivative of the denominator, we will get a limit of -5. So we're not done yet, but we're close. Remember that we're trying to find the limit of this expression that we called y. We don't have the limit of y on the left. We have natural log limit y on the left. So what do we do to both sides?
Exponentiate.
Exponentiate, so that we have limit y on the left as x goes to infinity. And we exponentiate, we get e to the -5. So that is our limit.
Oh, the sequence?
That is the limit of the sequence.
Wow.
So the limit of that. So that is e to the -5, that limit.
And we had,
That was what?
So complicated.
It is very complicated using log limit.
That is a lot of that.
There's a lot of algebra, which you guys are going to get better and better at.
Oh, man.
Masters of algebra.
And I thought the exams would take less pages as time went on.
Yeah, right? Not quite. All right, let's do one more of these.
I haven't seen much either.
Is there a spot there that anyone has a question?
Like the whole-
All right?
Is log limit always gonna be equal to something? If it-
No. Not always, but usually. It's possible to do log limit and end up with something different. But a lot of these that we are going to see in here, this indeterminate form 1 to infinity often does include an e. It doesn't have to, but often it does. Most of the time it does. Not all, it doesn't have to though. So here's another one. Let's do one more. I think we're going to do one. Yeah, we can do one more. So because we have to do a derivative, we know that there's going to be a derivative coming. So usually, if you're uptight about the difference between continuity and discrete, you like to switch it to an x. And then we take the natural log of both sides. And when we take the natural log of the right, the x drifts down in front using a log property. So that's the first step with log limit. Log of both sides, bring down the exponent. Now we take the limit of both sides. And as you do more and more of these, you just start writing the limit inside on the left right away. The limit can move right through log functions because the log is continuous. So we can invoke the limit superpower. It can move through continuous functions. And then on the right-hand side, we also take the limit as x goes to infinity. On the right-hand side, if we have a little bit of foresight, we see that this is going to infinity. We see that this is going to 0. Our goal is we'd like to get to L'Hopital. If we'd like to get to L'Hopital, we're going to shove the x in the denominator. And so you can kind of speed up your process a little bit by sort of doing it right off the bat.
Is the fact that you can move the limit symbol into the natural log something that can be actually proved, or was that just
You
declared
proved it in Calc 1.
axiomatically?
In Calc 1, you showed that the limit of a continuous function, you showed that the limit of a continuous function can push the limit in. That's what justifies all this kind of thing, like right here. The limit of this is the limit of the numerator divided by the limit of the denominator. So that limit is being pushed into the division function. A rational function, we have a continuous, this is a continuous function. So that you've used it a ton, maybe not knowing that you're using it. But anytime you have a continuous function, you can push the limit inside. Like if you have the square root of something, you push the limit through the square root. If you have like sine of something, you push the limit into the angle. So that limit has always had the power to push right into the inside of a continuous function. Okay, so now we are set here. Now we have L'Hopital's rule that we can use. So here we have the indeterminate form 0 over 0. You can put an L comma H there, whatever, or L apostrophe H for L'Hopital. And, all right, again, the denominator is easier to take the derivative of. So let's do that first. We're going to have limit. The derivative of the denominator becomes that. The numerator, derivative of a log, is 1 over the inside. So 1 over the inside multiplied by the derivative of the inside. The derivative of the inside, derivative of 1 is 0. This is negative 4x to the negative 1. So its derivative is positive 4x to the negative 2. In other words, we could write it like that. So that's the derivative of the inside. So this whole right-hand side, let's go ahead and simplify it. It's probably easiest if we, at least in the beginning, if we just write everything as a product of fractions. So that's where we're at. And if we just write everything as product of fractions, usually it's pretty easy to simplify it. So we end up with a -4 in the numerator and 1 minus 4 over x in the denominator. So here's where we are going to use that property that limits of continuous functions. You can move it through, you can push the limit into the bottom. And then when you push the limit into the bottom, you can separate it into two limits. So we're using limit properties. And what is the limit of the numerator? Limit of a constant is itself. Limit of a constant is itself. Push the limit into the denominator. The limit of the denominator is 1, because 4 over x goes to 0. So our overall limit is -4. So now we have the value of the natural log of the limit of y. We want the limit of y. So what are we doing to both sides? We're going to exponentiate both sides. So e to the -4. So that, oh, here he is. There, that's perfect timing. Aaron is going to speak to you for a minute about being an SI and making so much money.
You know, you guys have been telling you the same thing they told me when I taught my first class. You're not going to get rich doing this.
But it's going to be so rewarding.
But it's going to be so rewarding. Okay, so I'm in Calc 2, right?
Yes.
Okay, so I'm with dedicated math people. All right, dedicated math people. Who's going to a 4-year program? Nice. Who's going to grad school? Okay, a couple of hands. Who's going to teach? No math teachers in the room? There we go.
There's one, I
Okay.
count.
Okay, so guys, I'm starting with a lot of the reasons of why